Hello everyone, welcome to my honors option video for EME 303. Today, I will be introducing you with some of the basic ideas of compressible flow. Why I chose this topic? It is a hard process to think of a fluid mechanics related topic that's both interesting and understandable with my current level of knowledge. It was a complete coincidence that one day, when I was reading news, an article regarding the carbon sand equation regarding subsonic compressible flow over airfoils while I was browsing, and thought that it was an interesting topic to look into. I also think that since we only consider flows with incompressible fluids in class, it would be beneficial to us to review some of the basic ideas of compressible flow. Compressible flows are more practical and more applicable to real-life scenarios. Compressible flow is a widely studied topic in areas such as PNGE, mechanical engineering, and aerospace engineering. Before getting into the study of compressible flow, let's first start off with some background information about compressible flow. Compressible flow, unlike incompressible flow, which deals with fluid with general constant density, deals with fluid flows that changes its density significantly, usually gas. To distinguish if the flow is compressible, one has to look at the Mach number. Most relevant fields of science study involving compressible flows would be the manufacturing of rockets, high-speed planes, and sports cars. Referring to the picture below, a water fountain was made possible because of the incompressibility of water. If the fluid were changed to a compressible fluid, a water fountain wouldn't exist. In the previous slide, we mentioned that we will rely on the Mach number to determine if a fluid is compressible or not. The Mach number was a significant contribution of the Czech-Austrian physicist Ernest Mach. The Mach number is a dimensionless number used to express the ratio of local velocity to the local speed of sound. It has an equation of m equals to v divided by c, where v represents the local velocity and c represents the speed of sound. We classify flows with a m greater than 0.3 as compressible flow. Referring to the picture above, a schematic representation of the varying Mach numbers around a cross-sectional diagram around a wing is displayed. Two basic phenomena of compressible flow are choke flow and shock waves. Applications of choke flow are nozzles and diffusers. As we learned previously in class, flows of high and low velocities in nozzles and diffusers are adjusted interchangeably through the restriction of the exit. Another phenomena would be shock waves. Examples would be sound wave created by explosions, high-speed plane passing, and gun firing, when a wave moves faster than the local speed of sound in the fluid, in this case, air. Referring to the graph on the lower left, a fighter jet traveling at a speed of Mach greater than 1.2 would compress the air, since air is a compressible fluid, and then break the compacted air layers, causing what is known as the breaking of the sound barrier. Referring to the graph on the lower right is a classification of speeds of varying Mach numbers. There are two general classifications of compressible flow, one-dimensional flow and two-dimensional flow. We will start off with some of the basic ideas of one-dimensional flow. One-dimensional flows refer to the kind of flow that a diffuser or nozzle will give. As we studied in class, the exit of a nozzle has reduced cross-sectional area compared to the inlet, thus giving the incompressible fluid jet a higher exiting velocity. The opposite applies for the diffuser. However, when we are dealing with compressible fluid flows, the phenomenon described above might not be always true. Consider the following equation. dA divided by A is equal to dV divided by V times m squared minus 1 in parentheses, in which dV is the differential change in velocity, A is the inlet cross-sectional area, m is the Mach number, V is the velocity of the flow, and dA is the change of the area of the outlet. According to the above equation, when the flow velocity is less than 1 Mach number, A nozzle will increase the exceeding velocity, and a diffuser will decrease the exceeding velocity by the following derivation. dV is equal to V times dA divided by A times m squared minus 1 in parentheses. For subsonic flows with m less than 1, dA less than 0, dV will be greater than 0. A nozzle will indeed increase the fluid velocity, and a diffuser with m less than 1, dA greater than 0, will result in a dV less than 0, and indeed decreases the fluid velocity. However, when we increase the flow velocity from subsonic, which is m less than 0.8, to supersonic, which is m greater than 1.2, the reverse happens. Due to the flipping signs of the m squared minus 1 term in the equation, when a greater than 1 Mach number is incorporated, supersonic flows with m greater than 1, dA less than 0, results in a dV less than 0. A nozzle will decrease the fluid velocity, and a diffuser with m greater than 1, dA greater than 0, and dV greater than 0 will increase the fluid velocity, as opposed to subsonic flow behaviors. Before getting into two-dimensional flows, we need to introduce another one-dimensional flow concept, which is known as the normal shock wave. Cited from Wikipedia, normal shock waves are shock waves that are perpendicular to the local flow direction. These shock waves occur when pressure waves build up and coalesce into an extremely thin shock wave that converts useful energy into heat. The waves thus overtake and reinforce one another, forming a finite shock wave from an infinite series of infinitesimal sound waves. Referring to the graph below, we can see how shock waves behave under different speeds of Mach numbers. Two-dimensional flows are more inclusive. One of the major topics in two-dimensional flows is the oblique shock wave, which the normal shock wave is a subclass of. More commonly and widely studied, oblique shock waves are encountered when, for example, planes traveling in supersonic velocities. Practically speaking, there always exist disturbances around objects. Thus, with a non-zero disturbance angle sigma shown in the following graph, shock waves become oblique rather than normal. Based on the level of flow deflection, oblique shocks are characterized as either strong or weak. Strong shocks are characterized by larger deflection and more entropy loss across a shock, with the weak shocks as the opposite. In order to gain insight into differences in these shocks, a shock polar diagram like the one attached can be used. With the static temperature after the shock, T*, known, the speed of sound after the shock is defined as A* is equal to the square root of gamma times R times T*, in which A* is equal to the speed of sound after the shock. Gamma is the specific heat ratio, R is the gas constant, and T* is the temperature after shock. The Mach number is then broken down into xy components in the Cartesian coordinate system. M2*x is equal to Vx divided by A*, and M2*y is equal to Vy divided by A*, in which Vx is the fluid velocity in the x direction, and Vy is the fluid velocity in the y direction. So, what are some of the real-life applications of compressible fluid flow concept? One of the most common real-life applications of compressible flow concept is the construction of wind tunnels. They're used in the study of the effect of air moving past solid objects. As you can see in the graph attached below, this shows a model with helium-filled bubbles showing path lines of the wingtip vortices in a wind tunnel. Fighter jets also incorporate a very important concept we just discussed. Jets flying in supersonic velocities often adopt the designing concept of inlets. These inlets slow incoming supersonic flow before it enters the engine, with the caveat of minimizing losses across the shock. Between taking off, maneuvering, and cruising, an aircraft travels at a range of Mach numbers. In order to ensure efficient flight, the aircraft intake must be capable of variable geometry. If it's not, the shock wave will not reflect properly through the inlet and negatively affect performance. The graph attached below is the Russian Tu-160 strategic bomber, incorporating 4 big inlets to assist flying at supersonic velocities. Thank you for watching this video. I'm glad that I had a chance to complete my honors option project in EME 303 with such an interesting topic. The studies of compressible flow are far beyond what I just briefed about. I hope you will be interested in this topic by my short introduction. Thank you.